Okay, in this example, we have got a boundary value problem governed by a second order linear ODE. We want the solution in the domain x between 0 and 1. Epsilon is a small positive parameter. Okay, so following the same routine as before, we're going to start by working out the outer solution. So here we're going to seek a solution in the form of a regular perturbation expansion as follows. Then if we substitute and compare terms, coefficients of powers of epsilon at order 1, we're going to have your reduced equation. The solution of this was y naught equal to a to the power negative x. Now we've got a first order ODE here, and we've got two boundary conditions, so this can only satisfy one of them, and then the other one is going to give us a clue about the boundary layer location, right? So well, if we there's going to be a bit of trial and error here, but we'll sort this in subsequent videos. So if we fit the condition at x equals to 0, this tells us that a must be equal to 0, and so this gives us a trivial solution. Trivial solutions we don't like very much, so we are going to discard this option here. And then if we fit the other condition at x equals to 1, this one tells us that a must be equal to e, and therefore y naught is going to be e to the power 1 minus x. So this is telling us that the outer solution is going to be valid at the x equal to 1 end, and so it implies that the boundary layer is going to be at the x equal to 0 end. Okay, then if we continue with our outer solution at order epsilon, the governing equation is going to be y naught double prime plus 2y1 prime plus 2y1 equal to 0. If we plug in y naught here and rearrange, it's going to give us y1 prime plus y1 is negative 1/2 e to the 1 minus x. The condition at for y1 is going to be that when x equals to 1, y1 must be equal to 0. Then solving this subject to that condition gives us y1 is 1/2 into 1 minus x e to the power 1 minus x. So up to order epsilon, our outer solution is going to look as follows. So we're going to have e to the 1 minus x plus epsilon over 2 1 minus x e to the 1 minus x, and then there is going to be other terms. So this is our outer solution. Then next we turn into the inner region, which is in the vicinity of x equal to 0. So again we are going to introduce a scaled variable. This is similar to what we did in the previous problem. So we're going to write x equal to epsilon to the power alpha xi, and the dependent variable we are going to introduce capital Y in the inner region. The derivatives are going to look as follows. We've already seen that the first order derivative looks like this. The second order derivative follows suit. So that's going to be epsilon to the power minus 2 alpha, second order derivative of that. So the ODE is going to become epsilon to the power 1 minus 2 alpha y double prime, where now prime stands for derivatives with respect to xi, y prime here plus 2y equal to 0. Now since this is applicable in the neighborhood of 0, that is going to be the boundary condition. Then we go through the same process of finding a distinguished limit value for alpha. So here we're just going to mention that the distinguished limit is obtained by balancing term 1 and term 2, and it gives alpha equal to 1. Okay, the ODE then becomes y double prime over epsilon to y prime over epsilon plus 2y equal to 0. Multiplying through by epsilon gives this rescaled ODE, and the condition is still going to be this one. And then we look for a regular perturbation expansion inside this rescaled problem. So we seek y equals to y naught plus epsilon y1, etc. So if we substitute, so this is going to give us at order 1, we are going to get y naught double prime plus 2y naught prime equal to 0, subject to when epsilon equal to 0, the y naught is equal to 0 as well. Solving this is going to give us y naught is equals to a into 1 minus e to the minus 2xi. Now notice here that we have got a second order ODE and only one condition to fit. So out of the two constants we get from here, only one will be determined. So that's why this is involving a constant which is yet to be determined. This constant is going to be determined by matching with the outer solution at this order. Okay, so at this point we proceed to find a solution at order epsilon. The ODE is going to be y double prime y1 plus 2y1 prime plus 2y naught equals to 0. Then substituting this in gives us the following ODE. So that's going to be 2a into e to the power minus 2xi minus 1. So this is a linear second order ODE with a non-homogeneous term this side. There are many ways of solving it. You solve it. We could just integrate here, and then we're going to have a first order ODE. But the main thing right now is that solving this gives us the following solution. So D is a constant that again we still need to find. A is the constant that we already know about, 1 plus e to the minus 2 epsilon 2xi. So we have got our y naught, we have got our y1. So the inner solution we can write as y naught plus epsilon y1, but it still involves undetermined coefficients. How do we find these coefficients? Like I've already mentioned, we find the coefficients. Let's just write this out. The constants A and D are determined by matching with the outer solution. So in the next video we are going to look at a criteria of matching the inner and the outer solutions, and then using that criterion we are going to determine the values of A and B.